Prove Lensmaker's formula. Prove Lensmaker's formula for a convex lens. This is a diagram of convex lens. This is the convex lens. This is the convex lens. And we can denote an object point O1 be an object point placed on the principal axis of the convex lens. O1 be the object point placed on the principal axis of the convex lens. And we can denote the optical center. O is the optical center of the lens. Here O is the optical center, no deviation point, optical center of the lens. This is the principal axis. This is the principal axis of the convex lens. This straight line is the principal axis of the convex lens, and a ray is traveling. A ray from object point O1 is traveling along this direction, and this is the incident ray. And this incident ray is incident at the point A on the fast refracting surface of the convex lens, and the object point O1 exists in the surrounding medium of refractive index mu1. In this case, object point O1 exists in the rarer medium of refractive index mu1. Similarly, the surrounding medium on the other side is also mu1. Mu2 is the refractive index of the material of the convex lens. Mu2 is the refractive index of the material of the convex lens. And now we can denote the center of curvature, that is C1 is the center of curvature of fast refracting surface xp1y. C1 is the center of curvature of the fast refracting surface xp1y of the convex lens. We can denote fast refracting surface, that is xp1y, where p1 is the pole of the first refracting surface. Now we can connect the point of incidence A and C1, center of curvature, and that will be the radius of curvature, and this is also the normal. AN is the normal at the point of incidence A. AN is the normal. Now refracted ray will be traveling along this direction through the lens. After refraction through the lens, the refracted ray will appear to travel along this direction. In this case, this is the direction along which refracted ray will be traveling after refraction through the lens, and this is the direction of refracted ray. And the refracted ray, this refracted ray will form real image at the point I1 on the principal axis of the lens. I1 is the real image formed by the refracted ray. I1 is a real image formed on the principal axis and due to refraction of light through the lens. We can denote the real image I1. Real image I1 due to refraction of light through the fast refracting surface xp1y of the convex lens. And actually this ray will appear to travel along AI1. I1 is the real image point. I1 is the real image point due to refraction of light. Due to refraction of light through the first refracting surface xp1y of the convex lens. Real image I1 is the real image point due to refraction of light through the first refracting surface xp1y. And if we consider that the lens has second refracting surface. In that case, after refraction of light through the second refracting surface xp2y, refracted ray will be moving along this direction, and this refracted ray will form final real image I, final image point I, and this is I is the real image. I is the final real image due to refraction of light through the second refracting surface xp2y, and we can denote the distance of object point O1 from the first refracting surface xp1y. This is the distance of object point O1. Now we can denote the thickness of the lens. 2t is the thickness of the lens. 2t is the thickness of the convex lens. 2t is the thickness of the convex lens. And in this case, incident ray is traveling along OA, and refracted ray will be traveling along BI1, and I1 will be the real image point due to refraction of light through first refracting surface. Now, we can denote the real image distance, distance of real image I1 from the first refracting surface. Here V1 is the distance of real image point I1 from the first refracting surface xp1y. Similarly, we can denote the radius of curvature of the first refracting surface P1C1, which is equal to R1. R1 is the radius of curvature of the first refracting surface xp1y. With respect to the first refracting surface xp1y, O1 be the object point, and we can denote the distance of object point O1 from the optical center O. This is the object distance of the object point O1 from the optical center O of the convex lens. U is the object distance of object point O1 from the optical center O. U is the object distance. U is the object distance which is measured from the optical center O. From the optical center O. Now, if we consider the second refracting surface xp2y, I1 will be the virtual object. I1 is the real image with respect to the first refracting surface, but I1 is a virtual object with respect to second refracting surface. Distance of the object distance of virtual object I1 from the second refracting surface xp2y is U2. U2 is the virtual object distance from the second refracting surface. Now we can denote the distance of real image point I from the second refracting surface. That should be V2. V2 is the image distance of real image point I from the second refracting surface xp2y. V2 is the real image distance from the second refracting surface. Now we can denote second principal focus of the lens. F2 is the second principal focus. F2 is the second principal focus of the convex lens, which is the midpoint of optical center O and center of curvature C1 of the first refracting surface. F2 is the second principal focus. We can denote the focal length of the convex lens, that is the distance of second principal focus F2 from the optical center O. Here small f in lowercase, is the focal length of the convex lens. Small f is the focal length, that is the distance of second principal focus F2 from the optical center O. F is the focal length of the convex lens. Now we can denote the final image. I is the final image. I is the real image, and that is also the final real image formed by the two refracting surfaces. That means I is the final image formed by the convex lens with respect to the objective point O1. I is the final image. We can denote final image distance from the optical center O. This is the image distance of final real image I from the optical center O of the convex lens. This is the final image distance from the optical center. V is the final image distance from the optical center of the convex lens. Let O1 be the real object point. O1 be an object point on the principal axis of the convex lens. O1 be an object point existing on the principal axis of a convex lens. A ray of light from the object point O1. A ray of light from the object point O1 will be incident. A ray of light from the object point O1 is incident at the point of incidence A, on the fast refracting surface xp1y of the convex lens. A ray of light from the object point O1 is incident at the point A on the first refracting surface xp1y of the convex lens. xp1y of the convex lens. Now we can consider that the fast refracting surface xp1y encloses the denser medium of refractive index mu2, which is the material of the lens. Incident ray is traveling along this direction, and the refracted ray after refraction through the fast refracting surface in the denser medium of refractive index mu2 will form a real image I1 at a distance V1 in the denser medium, assuming that there is no second refracting surface. Only the fast refracting surface xp1y encloses the denser medium of refractive index mu1, and the refracted ray in denser medium forms real image I1 in the denser medium of refractive index mu2. And we can denote the object distance of the object point O1 from the fast refracting surface. E1 is the object distance of the object point O1 from the fast refracting surface xp1y, and also we can denote the image distance of the real image I1 formed in denser medium of refractive index mu2. V1 is the real image distance or image distance of the real image point I1 from the fast refracting surface, provided there is no second refracting surface, and refracted ray AB will form real image I1 in the denser medium mu2. The refracted ray AB. The refracted ray AB in the lens. The refracted ray AB in the lens will appear to travel along BI1 and forms a real image I1. In this case, the refracted ray AB will be traveling along AB, or will be traveling along ABI1 and forms real image I1 in the denser medium of refractive index mu2, provided there is no second refracting surface and the object point O1 exists in the rarer medium of refractive index mu1. The refracted ray, the refracted ray, the refracted The refracted ray AB. The refracted ray AB will appear to travel along AI1 in the denser medium of refractive index mu2, which is the material of the lens. The refracted ray AB will appear to travel along AI1 in denser medium and forms a real image I1 at a distance V1 from the fast refracting surface, and forms a real image I1 on the principal axis in the denser medium of refractive index mu2. Form a real image and will appear to form a real image I1 on the principal axis of the convex lens. The refracted ray AB will appear to travel along AI1 in the denser medium, provided there is no second refracting surface and will appear to form real image I1 on the principal axis of the lens. The relation between the object distance, image distance, relation between the object distance, image distance, and radius of curvature, image distance and radius of curvature radius of curvature for the image I1 and the object point O1 due to refraction of light through the first refracting surface XP1y. Relation between the object distance, image distance and radius of curvature due to refraction of light through the first refracting surface XP1y through the first refracting surface XP1y, provided this first refracting surface XP1y encloses denser medium of refractive index mu2 and there is no second refracting surface. Relation between object distance, image distance and radius of curvature due to refraction of light is mu2 by v1 is the relation is mu2 by v1 minus mu1 by u is equal to mu2 minus mu1 whole divided by r1 is equal to mu2 minus mu1 whole divided by r1. So r1 is the radius of curvature of the first refracting surface and we get the equation 1 which is mu2 by v1 minus mu1 by u1 is equal to mu2 minus mu1 divided by r1 which is equation 1 where r1 is the radius of curvature of first refracting surface xp1y of the lens. This is the equation 1. This is the equation 1. Now the refracted ray AB. Now the refracted ray AB will be refracted through the second refracting surface XP2y and this refracted ray will be traveling along BI in the surrounding medium of refractive index mu1. The refracted ray AB inside the lens will be the refracted ray AB inside the lens will be refracted the refracted ray AB inside the lens will be traveling along BI in the surrounding medium of refractive index mu1. The refracted ray AB will be traveling along BI in the surrounding medium of refractive index mu1 after refraction through the second refracting surface XP2y. After refraction through the second refracting surface or second refracting surface XP2y of the convex lens. Second refracting surface XP2y of the lens of refractive index mu1. The refracted ray AB will be traveling along the eye in the surrounding medium after refraction through the second surface and forms an image or forms a final real image. Forms the final real image I at a distance v2 from the second refracting surface and forms a real image I at a distance v2 from the second refracting surface xp2y of the lens. Second refracting surface xp2y of the lens. xp2y of the lens. xp2y of the lens. The refracted ray AB will behave as incident ray with respect to the second refracting surface xp2y. The refracted ray AB with respect to the first refracting surface xp1y The refracted ray AB with respect to the fast refracting surface XP1y will behave as or behaves as incident ray with respect to behaves as incident ray with respect to the second refracting surface xp2y, second refracting surface xp2y, second refracting surface xp2y, and a real image and the real image I1. The real image I1 with respect to the first refracting surface, assuming there is no second refracting surface. The real image I1, with respect to first refracting surface xp1y will be under bracket. The real image I1 with respect to first refracting surface appearing to exist in denser medium of refractive index mu2, provided there is no second refracting surface appearing to exist in denser medium of refractive index mu2, comma, will act as virtual object will act as virtual object. That means the real image I1 with respect to first refracting surface will act as virtual object with respect to the second refracting surface xp2y. Now xp1y is the first refracting surface. The refracted ray AB inside the lens will be incident at the point B on the second refracting surface xp2y, and this refracted ray AB will appear to travel along bi1 and forms a real image I1 with respect to the first refracting surface. But if we assume that there is second refracting surface xp2y, and this is the second refracting surface xp2y is the second refracting surface of the lens, second refracting surface of the lens, second refracting surface, and I1 is the real image with respect to first refracting surface. Similarly, I1 behaves as virtual object with respect to second refracting surface xp2y. I1 is the virtual object with respect to second refracting surface xp2y, existing in denser medium of refractive index mu2, and the final real image I is will be formed in rarer medium, that is in the surrounding medium of refractive index mu1. For the second surface xp2y, the virtual object I1, we have to assume that virtual object I1 exists in the denser medium of refractive index mu2, and the final real image exists in the rarer medium of refractive index mu1. The incident ray AB with respect to second refracting surface xp2y of the convex lens will be refracted along bi in the rarer medium, will be refracted along bi in the rarer medium of refractive index mu1, and forms real image I in the rarer medium, under bracket mu1 with respect to the virtual object I1 in the denser medium of refractive index mu2. Therefore, mu1 by v2 minus mu2 by u2 is equal to mu1 minus mu2, mu1 minus mu2 whole divided by r2, where r2 is the radius of curvature of the second refracting surface xp2y. Mu1 by v2 is equal to mu2 by u2, which is equal to mu1 minus mu2 divided by r2, which is equation 2, where u2 is the object distance. u2 is the object distance of the virtual object I1, appearing to exist in denser medium of refractive index mu2, which is the material of the lens. u2 is the object distance of the virtual object I1 appearing to exist in denser medium of refractive index mu2. mu2 is also the refractive index of the material of the lens. Now we can consider the second refracting surface xp2y, and the refracted ray AB will form virtual object at I1 at a distance u2 from the second refracting surface. I1 is the virtual object. Existing in the medium of refractive index mu2, and u2 is the object distance of virtual object I1. And in this case, the refracted ray from the point B after refraction through the second refracting surface will form final real image at I, and V2 is the image distance of final real image from the second refracting surface. I is the final real image which is at a distance V2 from the second refracting surface, and in this case real image exists in the medium of refractive index mu1, and virtual object exists in a medium of refractive index mu2. And that's why we should write mu1 by v2 minus mu2 by u2 equal mu1 minus mu2 divided by r2, where r2 is the radius of curvature of the second refracting surface xp2y. c2 is the center of curvature of second refracting surface, and r2 is the radius of curvature. R2 is the radius of curvature of the second refracting surface xp2y of the convex lens. Adding equations 1 and 2, we get mu2 by v1. Adding equations 1 and 2, we get mu2 by v1 minus mu1 by u1 plus mu1 by v2 minus mu2 by u2 is equal to mu2 minus mu1 whole divided by r1 plus mu1 minus mu2 whole divided by r2. And this is another equation. After adding equations 1 and 2, we get this, that is mu2 by v1 minus mu1 by u1 plus mu1 by v2 minus mu2 by u2 is equal to mu2 minus mu1 whole divided by r1 plus mu1 minus mu2 whole divided by r2. Now v1 is equal to u2 plus 2t. v1 is equal to u2 plus 2t, where 2t is the thickness of the convex lens. v1 is equal to u2 plus 2t, and v1 is the distance of I1 from P1, and 2t is the thickness, and ut is the object distance of virtual object I1 from the second refracting surface. This is u2. So therefore v1 is equal to u2 plus 2t. v1 is equal to u2 plus 2t for a thin lens. V1 2t is approximately equal to 0. Thickness can be assumed as 0. Therefore, V1 will be approximately, again, U1 is equal to U plus T. U1 is equal to U plus T. Therefore, U1 is approximately equal to U for a thin lens. U1 is equal to U plus T, and V2 is equal to, and V2 can be written as V minus T. Therefore, V2 is also approximately equal to V for a thin lens. For a thin lens, V1 equal to U2, U1 equal to U, and V2 is equal to V. Putting these values of V1, U1 and V2 in equation 3, putting these values of V1, U1 and V2 in equation 3, we get mu2 by U2 minus mu1 by U plus mu1 by V minus mu2 by U2 is equal to mu2 minus mu1 whole divided by R1 is equal to mu2 minus mu1 is equal to mu2 minus mu1 whole divided by R1. Mu2 minus mu1 whole divided by R1 plus mu1 minus mu2 whole divided by R2. Mu1 minus mu2 whole divided by R2, or comma mu1 by V minus mu1 by U is equal to mu2 minus mu1 divided by R1 minus under bracket mu2 minus mu1 whole divided by R2, or comma mu1 is taken common, bracket open, mu1 1 by V minus 1 by U is equal to mu2 minus mu1 is taken common, under bracket 1 by R1 minus 1 by R2, or comma 1 by V minus 1 by U is equal to mu2 by mu1 minus 1 bracket closed into 1 by R1 minus 1 by R2, 1 by R1 minus 1 by R2. And that is, here V is the image distance of final image I from the optical center. This is V. And object distance U is the object distance of the object point O1 from the optical center O. So we have the image distance V and object distance U. Therefore, 1 by V minus 1 by U can be written as 1 mu2 minus 1 mu2 minus 1 into 1 by R1 minus 1 by R2. So we get 1 by V minus 1 by U, which is equal to 1 mu2 minus 1 into 1 by R1 minus 1 by R2, where relative refractive index of the material of the lens with respect to the surrounding medium, relative refractive index of the material of the lens with respect to surrounding medium is 1 mu2, which is equal to mu2 divided by mu1, mu2 divided by mu1. This is equation 4. When the object point O1, that is when the object is placed at infinity, when the object is placed O1, that means when the object O1 is placed at a distance infinity from the optical center or from the lens, the final real image I will be formed at the second principal focus f2 of the lens, at the second principal focus f2 of the lens, of the convex lens. Therefore, if U is equal infinity, V equal f, where f is the focal length. If U equal infinity, then V equal f. This is the convex lens, and we can denote second principal focus f2, and O is the optical center. Parallel rays are coming from infinity. That means the object point O1 is placed at infinity. U is equal to infinity if the incident rays are parallel rays, and after refraction through the lens, refracted ray will pass through the second principal focus. In this case, the refracted ray, after refraction through the convex lens, the rays or ray will pass through second principal focus, and image will be formed at focus. That's why V is equal if U equal infinity, and if we consider parallel incident parallel rays, object should be at infinity, and refracted rays will pass through the second principal focus, and final image I will be formed at the focus. Image is formed at the focus. That's why image distance V is equal infinity. If U equal infinity, then V is equal if V is not equal infinity. In this case, V or image distance V is equal to f. Using these relations in equation 4, we get 1 by f minus 1 by infinity which is equal to 1 mu 2 minus 1, which is equal to 1 mu 2 minus 1 into 1 by r1 minus 1 by r2. Or comma 1 by f minus 0 is equal mu minus 1 into 1 by r1 minus 1 by r2. Therefore, and where 1 mu 2 is equal to mu, therefore 1 by f is equal mu minus 1 into 1 by r1 minus 1 by r2. 1 by f is equal mu minus 1 into 1 by r1 minus 1 by r2. This is Lensmaker's formula. This is Lensmaker's formula for a convex lens. Hence, this formula is being proved. We get 1 by f equal mu minus 1 into 1 by r1 minus 1 by r2, and this is Lensmaker's formula, hence proved.